That's how it can learn to control the pose and the face images at the same time. But as many of us have realized that label data is very expensive, so to do it unsupervised in a supervised way is a much more sensible things to do. So in the literature of machine learning, there's a recent interest in what we call disentangled representation learning. I kind of touched on this in previous slides. But basically, what these models do, so this is, again, kind of state-of-the-art, beta BAE and InfoGAN, is that it learns completely unsupervised a representation that is disentangled. So, for example, let's look at the top row. So here, it learns the representation. It learns basically two latent vectors. One controls the identity, whether it's old man or something, and the second latent vector controls the pose. So from turning from left to right and things like that. So these are currently state of the art in terms of disentangled representation learning. So what we want to propose is HoloGAN, which, because it's a generative model, it can generate images. So that's good. Look sharp, so that's good. But we can also control the pose of the generated images without any label. Okay, so that's the key. So this is very different from other unsupervised GAN model in the sense that this model offers a level of control of what you can render or generate without using any extra label. So we use the same data set with other GAN models, but on top of generating pretty images, we offer a level of control of like how you can look at the image. So this is a very cartoonish diagram of the conditional GAN. So again, you have a generator, the G, which is in charge of generating images. You have a discriminator that's in charge of judging whether it's real or fake, so same old. So Z is a latent vector, is a noise vector that you sample, and you input some parameter theta, which in this case may be pose, maybe something, to control the generated images. The problem is you also have to supply the discriminator with this information during training. So you do need a label during training. For HoloGAN, again, you have a generator and discriminator. You also have a noise, in terms of the input of the generator, you also have a noise vector Z and a theta pose, so you can control the pose. But in terms of the discriminator, there's no additional information. It's only see a fake or real images. And if you notice the legend, the difference between if you look at the generator, so these guys only use 2D convolution, right, which is green. What we argue with HoloGAN is that actually images that we see in the world is basically a projection of a 3D world, right? Any images that we see are basically just a capture of the 3D world that we're living in. And whether we can use this information in the generator to help is the main proposal of HoloGAN. So again, back to basics. This is the same slide I showed before. Rendering. So now we're trying to phrase the generator as not just a generating images, but also as like a somehow rendering pipeline. Again, if you look at it, sorry, let's go back to this. So instead of directly generating 2D features from the noise vector, HoloGAN first generating 3D features, so it's like a 3D representation of the world, and then render it to generate images. So that's the core difference in the generator. And this is also back to the two insights that I showed before. Doing rotation with CNN is very hard. And in order to do rendering, you need both the 3D input and the 2D images out. So, okay, so this is the more detailed version of HoloGAN. So unlike any other image generation pipeline, we first generating 3D features, these are learned features, and then render in quotation mark, to generate the final images. I put render in the quotation mark because it's not like handcrafted rendering that we think about in computer graphics, but we treat rendering here as a mechanism to bridge between the 3D representation and the 2D representation. And now, because we're learning a 3D representation, we can freely manipulate it in terms of pose. We can rotate it around to control what is being generated by the 2D images. And only by adding this 3D kind of knowledge about feature in the network design, we say, oh, actually, you first have to learn something 3D first before you generate images. Only by adding this insight, we can fully disentangle the pose and the identity without any label. But only by saying, oh, actually, dude, there's a 3D world that you have to learn first. The model learns to disentangle pose and identity completely by its own. And we train HoloGAN completely with a normal GAN loss. So there are a lot of literature on like the best GAN loss to use, but here we just use the basic one. I won't go to this part because it's kind of an implementation site, but I can talk to you over lunch a bit more, but I skip this part for now. So to show how you, so we train HoloGAN on different data sets with increasing complexity. What I mean by that is you first have a synthetic data set phase, so that's the easiest you can go for, synthetic, less complexity, so that's good. Phase, very highly structured, so that's a good test data set to start with. And then we basically starting moving to more complex and more basically real photos and see how it can cope with this. Again, all of this data set don't have any label. It's literally just random images from Google you can pull. So it's not the same. The images don't have the same identity. So all faces of different people, for example, they have different poses. We don't know what poses that is. So yeah, so it's completely different random photos. So we try with cats because everyone loves cats in machine learning. So here, I mean the resolution is a bit low, but I hope you can see that here you can generate photos of cat faces at any pose that you want. Here I just gradually rotate the faces from left to right to show that even though we keep the cat the same, but we can generate different angle of the face of the cats. So that's good. The next frontier is setup A, which is another famous data set. So here, again, as we rotate the faces, we can generate images of face of the same face from different poses without using any information of pose during training. So all this see is that a bunch of face images. And this covers this representation of face from different angles all by itself. And that's how we can rotate the face and generate the face from different angles as we want. So this is